So all of the reactions that we've seen this term have involved some sort of intermediates that involve cations or anions or radicals, right? There are a bunch of reactions in organic chemistry that don't fall into those categories. You don't have an ionic intermediate or you don't have a radical intermediate. And these are typically referred to as pericyclic reactions. And so I'll show you guys the three main classes for pericyclic reactions. The first one's Cyclo Addition. And we're going to spend a lot of time talking about Cyclo Addition reactions, but I'll show you guys the classic one. This is our Diels Alder reaction, where we have some sort of diene, and then we call this our dienophile. So let's make some notes. This is simply called a diene because it's got 2 pi bonds in it. And then the dienophile is the thing that wants the diene. And in this reaction, it's pretty straightforward. Oftentimes I connect the bonds with this dash bond, and this pi bond will break, hop over, and form a new covalent bond between those 2 fragments. The pi bond here will break and then form a new pi bond on the adjacent carbon-carbon bond. And then this pi bond will hop down and form a new covalent bond. So Cyclo Addition reactions are a really common way for making new covalent carbon-carbon bonds, right? And in this case, there's a huge variety of these reactions, but we're going to focus primarily on the Diels-Alder reactions. These are commonly referred to as 4+2 Cyclo Additions because our diene's got 4 atoms with 2 pi bonds, and your dienophile's got 2 atoms. So 4 atoms plus 2 atoms, we call it a 4+2 Cyclo Addition. All right, there's also another variant of this, which is called an electrocyclic reaction. And with electrocyclic reactions, you don't have 2 different pieces coming together. Instead, you just have one conjugated fragment that's essentially reacting with itself. So let's take this as an example. This is fully conjugated. We've got a triene. And in this case, it's going to form a new covalent bond where this dash is. So this pi bond will hop down, form a new covalent bond. This pi bond over here will hop over and form a new pi bond at that carbon-carbon position. And then this pi bond will hop over here. So when all is said and done, you're forming a new ring system. And you've got 2 pi bonds over on this end. So can you guys kind of follow that flow of electrons? Yep.
Is this an intermediate then?
What's that?
Is this just an intermediate then that just happens? Or the conditions?
It happens under specific conditions. We're not going to get into these reactions too much, but depending on the reaction conditions, your stereochemistry will change a lot. So you can do this reaction thermally or using light, and you get different products depending on which conditions you use. We're going to spend our time focusing on the Cyclo Addition reactions above, though.
It's stable enough to work under certain conditions. You can keep it like that.
Yes, you can make the triene and then form the ring system by favoring it under high heat or a specific type of light. In order to do these electrocyclic reactions, it's really important, though, that you've got a conjugated starting material. All right, and then we do have some reactions that don't really fall into the Cyclo Addition category or the electrocyclic reaction category, and these are called Sigmatropic Rearrangements. And with sigmatropic rearrangement, instead of having a conjugated starting material, you have a non-conjugated starting material. So I'll do the analog to what we just saw. Oh, let me clean this up. There we go. So this is non-conjugated. And in this case, I'm actually going to throw on 2 methyl groups over here. So let's see what happens when this undergoes the rearrangement. We're going to form a new covalent bond here, and this pi bond will hop down to form that covalent bond. This other pi bond will hop over to form a pi bond, and then this covalent bond will actually pop over to form a new pi bond. Whoops. So these reactions are kind of like flipping the molecule inside out, so to speak. Actually, I'm going to move this. Whoa. The pen is not liking this. There we go. So essentially we formed a new covalent bond on this side, or a new sigma bond, I should say. Why do you think this rearrangement is favorable? Anybody have an idea?
More stable alkene.
Yeah, exactly. If we look at our product, our alkenes are di-substituted versus our starting material where they're mono-substituted. So this will occur spontaneously, and it typically favors the thermodynamic product as a product of the sigmatropic rearrangement. This also follows the same rules with electrocyclic reactions where you can get some unique stereochemistry depending on whether or not it's done with light or heat. I would recommend reading the textbook portion of that if you're curious, but it's not something I'm going to test you guys on. Are there any questions with these reactions? All right, now we get to get into the good stuff. We'll do the Diels Alder reaction. So we said with the Diels Alder reaction, you need to have this diene and a dienophile. And it's got a bunch of very important rules. The first part is this diene has to be in a specific conformation. What conformation would we call this? S-cis, right? So it's single bond cis, meaning those two pi bonds are on the same side. So this would be an S-cis diene. It will not work with S-trans dienes for a lot of reasons, mainly because sterically you don't have enough overlap to perform the Diels-Alder reaction, and it's a lot more stable when it's in the S-trans conformation. We destabilize it by forcing it into that S-cis conformation. Okay, and then we're going to take our dienophile, and in this case, I'm going to call this EWG and EWG. These are for electron withdrawing groups. Oftentimes your diene needs to be electron rich and your dienophile needs to be electron poor. So in this case we'll write electron poor, electron rich. However, there are some Diels-Alder reactions that are called inverse demand Diels-Alder reaction where your diene can be electron poor and your dienophile can be electron rich. We're going to go with the classic one where your diene's electron rich and your dienophile is electron poor. So same sort of thing. I normally just connect the dots between my diene carbons and my dienophile carbons. And then we have the cyclic flow of electrons. So this pi bond's going to hop over, this pi bond's going to hop over, and this pi bond's going to hop over. So now when we do this, we formed a new six-membered ring. We've got a new pi bond on that far side. And then we've got electron withdrawing groups coming off the two carbons that were formerly the dienophile. So I'll call these EWGs. Do we have to worry about mixtures of enantiomers here?
No.
Why not?
Meso.
It's a meso compound, right? However, there are some situations where you do have to worry about mixtures of enantiomers, and we'll talk about that more later. So let's take a look at this with a short YouTube video. See if this will open up. And you can see that it's essentially like a docking. So this diene is on the right, your dienophile is on the left. Your diene will float over on top of your dienophile, and then you'll form these new covalent bonds and your pi bonds will shift over. So it's really important to think of this as three-dimensionally, as a stacking interaction, not a 2D side-on interaction, right? And we'll talk more about that 3D interaction in detail. It can be really tricky to draw though, so we'll spend some time practicing that. Okay, so let's do a little bit of practice here. Okay, for this practice problem, I've got a different looking diene. And I've got this dienophile over here where I've got nitrile groups coming off. And the first thing I always check is my diene to make sure that it's S-cis. In this case, we're locked into an S-cis conformation, so we don't have to worry about it, right? So let's try to predict the product we would get out of this reaction. And then check with your neighbor to see if you agree. I'm going to color code this because I can. Oh. How many of you are agreeing with your neighbor? A few people? All right, give me a thumbs up if you got it. All right, let's take a look. So we're going to connect the dots here and here. Pi bond hops over, pi bond hops over, pi bond hops over. Okay, so it looks like this blue ring is staying intact. However, that right-hand side of the blue ring is going to have a pi bond. And then let me switch to my purple pen here. And can you guys see how we formed these new pi bonds right here? Actually, I'll do them in red just so we can keep track of them. Between our dienophile and our diene. So in this case, you can use this to really rapidly build up ring sizes. So you can go from a monocyclic ring to a bicyclic ring system, or go from a non-cyclic ring system to a cyclic ring system. This is really important for natural product design. So if you're trying to make a new drug or a new medicine, oftentimes they have these weird, funky ring systems, and as a chemist, it's your job to figure out a way to make them. All right, let's do some other practice. Okay, let's try this one. What will the product be? What do you think the starting material is?
That's not SS.
Exactly. This is a good trick question that I like to throw at my students to see if they're paying attention. No reaction, right? This is S-trans. We said that Diels Alder reactions won't work unless you have the possibility of forming that S-cis conformer. So in this case, you're kind of dead in the water right here. You just recover your starting materials. It's a little tricky, but it's a common mistake that people miss. You have to have that S-cis conformation. So let's do a different example. Let's try this guy. All right, this isn't S-cis, but what can we do to drive it to the S-cis conformation?
Throw in energy.
Yeah, throw in energy, right? We said that there's a 15 kcal per mole rotational barrier, but we can push that. So we'll heat this up typically. So we'll do 15 kcal per mole. Now we're ready to go. So it's not that you're locked in that S-trans conformation, it's just that you need to add a little bit of oomph to it to get it to that S-cis. And then let's do a different dienophile. And I'm just going to call these R groups coming off. And then check with your neighbor to see if you agree. Then give me a thumbs up if you agree with your neighbor, or if you're very, very confident on your own. All right, so let's take a look. Just like before, we're going to connect the dots here. Your dienophile can be either an alkene or an alkyne, right? They both have pi bonds, so either of them can work. And in this case, we're just going to pull one of these pi bonds over. And this pi bond will come over, and this pi bond will come over. That means that our ring system that we have left over... Uh-oh. Come on. Oh my goodness. There we go. So we've got a pi bond on that far left-hand side. We've got one leftover pi bond on that far right side from our dienophile. And then these R groups are coming off both of those carbons. So you can have leftover pi bonds in your dienophile, and that's always important to remember. So for those R groups, right, they're stuck in one configuration. However, we will talk about stereochemistry and regiochemistry next. This is kind of our warm-up. The molecular orbital view for these reactions is pretty interesting. So imagine this guy over here is your diene, right? So our diene, if we think about the HOMO, we've got a pi bond right here, and we've got a pi bond right there. In order to dock with our dienophile, we're going to do this on-top interaction. In order for it to stack correctly, your dienophile actually has to be in phase with the molecular orbitals on your diene. So in order for that to occur, you actually have to interact your LUMO of your dienophile with your HOMO of your diene, if that makes any sense. Really all that's saying is that you have to have a red-on-red interaction with a blue-on-blue interaction. You actually can't have this react as a HOMO because both of those would be in phase with one another and they wouldn't stack correctly with the diene. We're not going to get too deep into the MO theory, but it is really important when you get into higher level chemistry, so I wanted to bring it up. Yeah, they talk about it a little bit in PChem. If you go on and you take things like inorganic chemistry or even advanced organic chemistry, they get into it in a lot more detail. All right, so now let's do stereochemistry and regiochemistry. This is the hard stuff. All right, the first part's pretty easy though. So let's just say we've got a cis dienophile. So I'm going to stick with a super generic diene, and our cis dienophile is going to have electron withdrawing groups coming off the same side, so I'll just call this CN and CN. Nitrile groups are really common electron withdrawing groups, but it could be an aldehyde, it could be an ester, it could be a ketone, anything that's pulling electron density away. And then we said when this occurs, you're going to connect these dots. This pi bond's going to hop over, this pi bond's going to hop over, this one's going to hop over. And then with your final product, these nitrile groups are going to be cis on your cyclohexene, right? So they're cis here. That means that they're going to be cis in your product as well. But let's take a look on the side-on view and our transition state. So imagine that this is our diene, right? And we're going to dock with our dienophile, which is kind of underneath. So I'm going to draw this underneath. Oop. And we're connecting, oh no, it's doing it again. So we're going to connect these dots right here and here. And then we're breaking this pi bond, so I'm going to show that as a dashed line. We're breaking this pi bond, so I'll show it as a dashed line. This pi bond's breaking, and then we're forming this pi bond over here. Oh my goodness. I hope I haven't damaged my laptop. So just like I said, you have to have this molecular orbital overlap in order for this to occur. And then when it comes out of this transition state, you're going to still... Actually, let me draw it a little bit differently. You're going to have kind of this almost house effect. Oh, oh my goodness. This is not good. Maybe this is a good excuse to upgrade. Sorry, guys. Ugh. I know. What do they call that when they like sell you an appliance with a limited lifespan, so you're forced to upgrade? It's like planned obsolescence. I think they do that with laptops. All right, so your nitrile group is going to be pointing down like this and down like this. These two molecules on that far right-hand side are equivalent to one another. So you may see the side-on view in your textbook or the top-down view. But if you think about it, right, the side-on view, if you're looking down on it like this, those nitriles are pointed away. And then, oh my goodness, your hydrogens are going to be coming out kind of like that. So your hydrogens are going to be wedges. Those nitrile groups are going to be dashes. All right, let's do the same thing with our trans diene. So do the same one that I have here, but instead of those nitriles being on the same side, do them on opposite sides. And I'll try to fix my laptop. There we go. Oh my goodness. So you've got one nitrile going this way and one going this way. Let's go ahead and connect our dots here. This pi bond we said is going to hop over. This one's going to hop over. And this one's going to hop over. And just like you guys probably thought, your cyclohexene is going to have the substituents trans to one another on the ring, right? I am almost ready to use the board right now. This is getting to be a bit much. The other thing you have to consider when you are running into these sorts of Diels-Alder reactions is the potential of forming multiple products. So in this case, you can imagine a possible enantiomer as well. In this case, this won't be enantiospecific, so you would observe a racemic mixture of products. So I'll write plus En over here as well. Does that make sense? Is this a meso compound? No, if you try to cut it in half, it's not. The one above it is a meso compound, so we don't have to worry about a mixture of stereoisomers. All right, one last one, and then we'll get into the more complicated examples. Let's do a tetrasubstituted. Okay, so we've got our S-cis diene, and I'm going to just stick with the same dienophile, but now we've got groups coming off all four positions. You can imagine, in this case, stereochemistry doesn't really matter that much. Because this pi bond, when it hops over, is going to form a new carbon-carbon bond, but that carbon-carbon bond's not going to have any stereochemistry anymore. So when you're all done drawing this, your final product's just going to have 4 groups coming off. You can show them as dashes and wedges if you want, but it really doesn't matter, so quite often people just don't even bother using dashes or wedges in these situations. All right, you guys want to try a more challenging one now?
Yes.
All right. So let's do this one. So instead of having weird functional groups coming off of our diene, I've kind of mixed up, or off of our dienophile, I've mixed up our diene a little bit. I'll show you guys some tricks for this too. I'm going to do that side-on view that I did before. Let me clean this up a little bit so we can see it better. Okay, so we're gonna definitely attach these 2 carbons still. This pi bond will hop over, this pi bond will hop over, and this pi bond will hop over. But let's see the transition state. So imagine that diene that I have drawn as being completely planar, even though it's kind of hard to see. We're forming a new covalent bond down here. Down here, this pi bond is breaking. This pi bond's breaking, this pi bond's breaking, and this pi bond's breaking. Right? So now the tricky thing is, let's switch this to a 2D side view for our product. We know these nitrile groups are going to be poking down kind of like this, and the hydrogens coming off of our dienophile will be more in that kind of equatorial-like position. And we know we formed a new pi bond over here, but the question is, which position will our methyl group be in? Will it be right here or right here? And then we've got a second methyl group coming off this carbon. Will it be right here or right here?
Right here.
Right here.
They both be on the top face,
Will they?
or they both be on the bottom face.
Oh. So talk about it with your neighbor and see if you guys agree.
The major one would be both on the top face, because it'd be easier for multiple levels to face energy. But I think as long as they both their loss shift places, trying to pull by pushing to the same face, it's just really fluid. It's just horrible. Oh, what's wow.
All right, I'll show you guys a different perspective in case you're struggling with this a little bit. I call this the top-down view. Some people hate this, but I'll only show it once. So imagine the dienes on top. So I'm going to show that as shaded. And your dienophile is kind of underneath it, so I'm going to draw that with a little bit of perspective further back. So can you guys kind of see how, with perspective, that dienophile is behind it? Okay. And the methyl group, we've got one of them that's kind of pointed in, so I'm going to draw the hydrogen going out, the methyl group going in, and then for the other one, the methyl group's going out, and the hydrogen's going in. Okay? We're forming a new covalent bond between these 2 carbons. This pi bond's breaking, this pi bond's breaking, this pi bond's breaking, and then we're forming a pi bond right here. Okay, so if you kind of think about this, right? This is similar to the conformation for cyclohexene chair flips where you have flagpoles. this methyl group and this hydrogen are sticking up kind of in the same face of that cyclohexane. So if we think about that, right, this methyl group over here is going to be different than this methyl group over here. One of them is going to be sticking up kind of away from the ring, and one's going to be sticking out away from the ring. It's a little bit hard to see sometimes, and it requires a fair amount of perspective. So let's try to draw this using our 3D view, or sorry, our 2D view. So we've got our 2D cyclohexene now. We've kind of figured out where our substituents should be coming off of. So just for the sake of argument, let's number this. I'll go 1, 2, 3, 4, 5, and 6. And then 1, 2, 3, 4, 5, and 6. So in that 3 position, should the hydrogen be a dash or a wedge? A wedge, right? It's coming out closer to your eye. So I'll say, all right, that means that the hydrogen, on the other hand, must be a dash. These nitrile groups are pointed down, so I'm going to make them dashes too. And then this methyl group is going to be a wedge. So you do have to pay attention to the positioning of substituents coming off of your diene as well as your dienophile. And sometimes it's a little hard to see unless you do kind of a side-on view or a top-down view of your molecule. Does that make sense? All right, now the main question that a lot of students will ask me when I'm doing this is, why do you always draw the cyano groups kind of going underneath rather than out and away? That's a lot harder to draw. Why are you putting me through this? Well, there's actually a fair reason for that. And this is called the Endo Rule. Oh, yeah. I mean, I want you guys to practice drawing. I don't grade you on artistic ability, though. I'm artistically challenged sometimes. So let's do this with an example. And I want you guys to help me first draw the overall product of this Diels-Alder reaction. And then we'll try to figure out the stereochemistry. So see if you can draw this using the best artistic ability that you have, and then compare with your neighbor. So I'll get us started here. I'm going to connect these. Got the circular rotation of pi bonds. We've formed 2 covalent bonds and 1 pi bond. So can you guys see how this carbon right here is kind of like a roof? So we formed a bicyclic ring system here. All right, and then on the other side, we've got this. But if you notice, we've got a ton of stereocenters here that I have not accounted for. If I'm going through and looking for stereocenters, I've got a stereocenter right here, stereocenter right here, stereocenter right here, and a stereocenter right here. Can you guys see that? I'm getting a few confused squints. Here, let's kind of color code things. Oop. So I'm going to color code my diene with the blue here. Oop. Oh no, not again. It's just going to be one of those days. So this is our diene that I've got highlighted in blue. And then we've formed this sigma bond and this sigma bond. Can you guys see that? Okay. So now let's take a look at this using kind of our side-on view that I like showing. So we'll do a side-on view for our intermediate, or actually, sorry, I'm using the wrong terminology, for the transition state. We'll try to account for those 4 stereocenters in our product. Okay, so I'll draw this ring system kind of side-on like that. So that's my diene kind of floating around. And then we've got our dienophile, which we know is kind of underneath. We've got 2 options. We could have it like this, where we're making and breaking all of these bonds. So that's one transition state. The other option is, instead of that second ring kind of pointing out in a way that it's stacked almost underneath, some people call it like an alien abduction. Let me make sure I draw this. Whoa. Okay. Okay, so in this example, we're docking kind of in an underneath fashion. Can you guys see that difference? Oh, sorry, this is kind of out of whack here. So can you guys kind of see the difference? One is stacking kind of side on, one's underneath and on top of. This is one of these interesting cases in chemistry where sterically you would think the one on the left would be more favorable, right? It's got less steric clash of things running into one another. However, electronically, the one on the right is actually more favorable, and that's simply due to this weird interaction that's occurring between these electron withdrawing groups. And so I'm just going to highlight this with a beautiful fluorescent pink. This is electronically stabilized. When your electron withdrawing group is underneath, you are dying. Okay, so we know that this one, if we go through and we were to draw our final product out of it, is going to have this weird two-dimensional structure. So I'm going to go ahead and try to draw this using two-dimensional features. Or sorry, 3D features. So we've got this roof over here. That roof is from this carbon, so it kind of flips up. We've formed this pi bond over here. And then underneath, we've got this weird 5-membered ring that's essentially sticking down. And then our hydrogens are kind of sticking out in a way. This substituent right here is referred to as your endo group. Endo means that it's closest to your longest bridgehead. So it's endo orientation. Means it's closest to the longest bridge. Typically, this endo conformation is preferred with Diels-Alder reactions. However, there are techniques to get exo favored. So this would be referred to as exo transition state. So I'll call this exo TS double dagger, and I'll call this endo TS double dagger. Usually that endo transition state's favored due to that electronic interaction. Yep.
Can we see the one on the left in the same kind of drawing as the one on the right?
Yeah, definitely. So we can do this side-on view of our bicyclic ring system. It looks similar where this bridgehead right here kind of flips up, but instead of that other 5-membered ring being pointed in that endo orientation, we're going to just have it kind of sticking out.
Isn't it still just as close as the bridgehead though?
That's a good question. So let me finish drawing this and then we'll talk about that. All right, so can you guys see how those are different from one another? So if we look at this one, the closest distance it has to is that 1-membered bridgehead, where this one up here is closest to that 2-membered bridge. So endo just means it's closest to the longer bridge in the bicyclic ring system. Can you guys see that? It's a little bit weird to see. Sometimes if you build the model, it's a little bit easier to decipher. It's really tough to draw some of these bicyclic ring systems using pen and paper.
So the longest one is the double bond at?
Yeah, you see how this is a 2-carbon bridge?
And we're comparing that with both of them, the distance between the two.
Yeah, exactly. So here we've got a 1-carbon bridge, which means that this is our exo substituent, where the one over there is endo. Usually our endo conformation is preferred. Does that make sense? I know this is a lot to digest. Let's try one more.
Actually, I have a question.
Yep.
Back to the very top of this endo-exo reaction.
Mhm.
What happens if I had my diene attack, or be it like rotate it 180 degrees and have the back do the attack? Would I get a different product? Or?
The back doing the attack for your dying?
Yeah, so the blue diene, I rotated it to make it easier to draw, and
It's a good question. It's really easy to mess these up unless you show your dying kind of facing your dienophile. So try to have both of the pi bonds and your dyene pointed towards your dienophile. If you orient them differently, it's really easy to kind of mess up the drawings. But this is kind of the preferred way of drawing it. All right, so now let's redraw this top one using correct stereochemistry, but in our 2D conformation. And let's draw our endo product. Whoops, sorry. So we said that that roof is kind of going to be flipped up, so I'm going to shade that using wedges. And then that 5-membered ring with the oxygens is going to be pointed back. So what you can do is you can show this using dashes if you want, like this. However, what you may notice in your textbook or in other chemical literature is this just kind of looks funny, having a dash go to a carbonyl. So in order to solve this problem, what they do is they just draw it as a straight line. And they say, well, if that's a dash, the hydrogen coming off that carbon is assumed to be what? A wedge, right? So it's a lot easier to draw it like this. And so you oftentimes don't see dashes or wedges going to carbonyls or endo or exo groups. You instead show stereochemistry of the hydrogen coming off instead. So that kind of shows that endo preference. All right, I think we are running out of time. So when we come back tomorrow, we'll talk about Regio Chemistry a little bit more. So that's specifically referring to which carbon's being attacked at which position. So we'll talk more about that tomorrow.
So when I asked about whether or not we had to draw them, I was referring to the side-on stuff. We're going to draw the side-on stuff?
You don't have to draw the side on, but the products you absolutely need.
Okay, oh, I see
Yeah.
the products.
Yeah.
I was asking about the